Hello chemistry students. So this is video 1 of 2. This weak acid strong base titration lesson will be broken up into 2 parts, so that at least 2 parts, maybe 3, but I'm thinking just 2, so that it doesn't go too long. Okay, so the first part is going to be just to review the concepts of titration, especially involving a weak acid with a strong base and a weak base with a strong acid. Then we will do one part of one of the example I have. Okay, without saying too much more, let's just get started, and we're going to jump right into it. So we are titrating here a weak acid with a strong base. Now we'll talk about the opposite, but for now we'll talk about a weak acid with a strong base. We know that weak acids, they only ionize partially. Okay, so they will have a certain Ka value. Okay, they only ionize partially. Now this must be considered in calculations. Okay, so what we're going to be working with in our example today is acetic acid, and so our weak acid, and sodium hydroxide as our strong base. Okay, now this is just comparing a titration curve that you saw in grade 11 versus one that you are going to now look at in grade 12. Okay, one that you're going to look at, and for your lab you're going to actually draw. Okay, so in grade 11, is strong acid, strong base titration, you saw that your endpoint was hopefully equal to your equivalence point, or indicated that your equivalence point was at 7, where the number of moles of hydrogen ions was equal to the number of moles of hydroxide ions, right? And it was a very gradual increase of your pH until a sudden increase into your equivalence point, right? Kind of hard to get that in the lab before over titrating, right? Now, in our case here, so we have a sudden increase. It's important to have that very sudden increase in pH, but only slightly, right? And then it begins to taper, and we see a very, very gradual plateauing here of pH due to, we'll talk about later, but called the buffer effect. Okay, your equivalence point here, notably your equivalence point is not at 7 like it was in grade 11. Notice your pH, and this isn't really, I don't really have a scale here, but your pH is just above. This is 7, just above 7. Now this is for a weak acid, strong base titration. So just above 7, we'll talk about why that is. So there are major differences here between these two curves. If you are at the end of this set of videos, hopefully you're able to explain what those differences are, and that would be a good sign that you understand what's going on. Okay, so a couple important points. Again, low Ka indicates that acetic acid only partially ionizes. Okay, what will happen? So this is showing you the ionization of acetic acid, hydrogen ions, and your acetate ions. Now, hydroxide ions will react with the acetate or with the acetic acid, right? It will neutralize in this titration. Importantly, though, what should follow that point is the more hydroxide you put in, despite it being a weak acid, the more hydroxide ions you put in, the more you force this reaction to move to the right. So that what will happen is that your acetic acid, despite it being weak, it will react quantitatively. That means your hydroxide ions will continue to consume hydrogen ions until your acetic acid has ionized completely. Okay, again, in context, it will make more sense. But essentially, adding a base to neutralize even your weak acid, despite it having a very low Ka value, will force the reaction forward as it is consuming hydrogen ions. Now that ties in with Le Chatelier, right? If this concentration is going down, then the reaction is going to move in the forward direction, reacting therefore quantitatively with hydroxide. Okay, again, in context, this will hopefully make more sense. Okay, already kind of talked about what's happening here. Take note of a sharp increase at the beginning, since the few hydrogen ions that are present, right, from the dissociation, the partial dissociation, ionization of your weak acid, since those are completely neutralized by your hydroxide ions, you see a spike in pH, but that begins to level off around here, your buffering region. Okay, we'll talk a little bit more about that. until you get to your equivalence point, and approximately in this example right here at 20 mils. Notice that your pH is not at 7, which is what you would expect it to be if it was a strong acid, strong base, but it is just above that, roughly just below 9. Okay, then you still get that same plateauing effect immediately after. Okay, so just a bit more on buffers here. We could have a whole other lesson on buffers, so that's not right now. I'm not going to talk about that right now. But what's happened here is that there is a buffer system that exists. Now, if you're taking grade 12 biology, hopefully that makes sense to you, right? So there's a buffering system that occurs here. Once a buffering capacity has been overcome, that's when you begin to get a faster increase in pH, more significant, notable increase in pH. Okay, so enough about buffers, that's another discussion. All right, we looked at a weak acid, strong base. Now this is a weak base with a strong acid. So similarly, you get a sudden, in this case, we're starting off with a higher pH, right, because it is basic. You get a sudden decrease then in pH as you have consumed those hydroxide ions by dropping in HCl, right? We start off with a weak base, strong acid here, right? Then we get a buffering region here. When it's past buffering capacity, you then reach your equivalence point, which if you notice, it's not at 7. So it's not at 7, not there. It's just below 7, so it's slightly more acidic. Okay, so think about why that might be the case. Going back to this example, what if I've written it here? I'll be sure to go over why, but for a weak acid, strong base, notice it's above, right? Think about a weak acid. Think about our conjugates here. Our weak acid produces a conjugate base. Now, if we look back at a previous lesson on the acidic and basic properties of salts, we looked at ions that are conjugate bases that came from a weak acid. They actually behave like bases, right? Keep that in mind. A little more on this later. Similarly, for a weak base, they produce conjugate acids that actually behave like acids. Therefore, we have a slightly more acidic equivalence point. Okay, now, if that doesn't make sense, that's okay, because these are really just clues. I haven't completely tied this all in yet. I'm just hopefully throwing out clues. Okay, there are 4 points. 4 points that we're going to go over in this lesson. In part 1 of the lesson, we're only going to go over the first point. Okay, so stay tuned for points 2, 3, and 4 to follow. But part 1, just our first point, as well as some of that background information there. Okay, our first point, fortunately, is really nothing new. We're going to use Ka or Kb if it's a base to determine what the pH is, right? So each of these 4 points, we're going to figure out what the pH is at each of these points. And what we're really using here is just equilibrium calculations or equilibrium skills we've learned in the past couple of weeks. Okay, so in this case we have a weak base again, just showing you that same graph. This should perhaps be a little bit sharper here, but we have a buffering region here, sudden drop off after buffering capacity. Notice we have a lower pH because of that conjugate acid present. Here's where I've detailed that. So the conjugate acid of your base, right, because that is your weak base, it hydrolyzes with water to produce hydrogen ions. That presence there at equivalence is the reason why we have a lower than normal pH for a weak base, strong acid titration. Okay, rewind that if you need to hear that again. Ask questions. Hopefully you're going through this video and you're writing down questions. Your question marks all over the place is okay. Try to answer them yourself by watching the video, practicing a bit, but certainly ask me. Okay, now let's get to some nitty-gritty details here. Okay, imagine yourself here just physically distancing before everything. Let's continue. So weak acid. This is a weak acid, strong base titration example. We're going to spend the rest of this lesson on this one example with the 4 points. Again, we're only going to do the first point. Okay, I do explain these points a bit more. Let me go back. So I do explain these points a bit more here, but I also have an accompanying study guide that I've written that goes over each of these points. So I'm not going to talk about this right now because we're looking at a different example that we're going to start. This is a weak base strong acid. I'm going to talk about now a weak acid strong base. Okay, so our first point is in a titration that involves 20 milliliters of a 0.3 molar concentration of acetic acid with, now standardized, we haven't gone over exactly what that means yet, but essentially it means a tested against a standard concentration, a tested concentration of sodium hydroxide. So essentially that just means a very accurate concentration of sodium hydroxide. So again, 20 mils of a 0.3 molar concentration of weak acid, 0.3 moles per liter of sodium hydroxide. Okay, so what is the amount of unreacted acetic acid, and more importantly, and the pH of the solution? So what is the pH at each of these 4 points? First point, before titration. Next point, during the titration, but before your equivalence point. Now here it tells you when 10 mils of base has reacted. Now sometimes it doesn't tell you that, and we'll go over examples that don't, and we'll solve them together. At the equivalence point, so at your equivalence point, here it tells you, again, you might come across examples that are questions that don't, so we'll figure that out. But here it says your equivalence point is reached at 20 mils of base. Finally, beyond equivalence point. And here is where we can make up a value, but we'll get to that in part 2 of the video. So for now, we're only going to do, in this part 1 video, we're going to do figure out just that first point. Okay, so before titration has started. So you have your pH probe in your lab, you've measured your pH here, but here we're doing it using a bit of math. So we're going to figure out the pH of the solution. In the flask, we know that there is a 0.3 molar concentration given to us. Okay, no stoichiometry to perform here. I say that for a reason. That will make more sense as we move on, so don't worry so much about this part here. But what's important for every point to think about is what are the major entities? What is present? What are all the ions and substances present at each of the points? So before titration, what we have is acetic acid. Now, acetic acid, it has ionized. Right? We do have hydrogen ions and acetate ions that are floating around, not much, right? Because it does have a very low Ka value. And we also have water present. Now, your Ka value is given to you in the problem. Your Ka value for acetic acid is 1.8 times 10 to the negative 5. Okay, so these are the ions that are present, and our Ka value plays an important role here because that will tell us how much of these, notably this, hydrogen ion we have at this point. Okay, so ice table. When you don't know what to do, or even if you do, draw an ice table, right? An ice table. So here's your ice table. We have a concentration of acetic acid. We have 0, for our products, right? For our ions at time 0. Then they change in proportion to the stoichiometric coefficients, which is 1, 1, 1. So it's just negative, positive, positive. Hopefully you're used to that. Then we add I and C, and we write E. And there we go. Okay, now our Ka expression will look like this. Okay, we can now plug in expressions. And since our hundreds rule applies, now again, you don't have to go through the proof of how it applies, as long as you do say it, so that it makes sense. Since your 100 rule applies, you can get rid of this x value. Okay, now all we're going to do here is solve for x. So notice that x is gone here, that minus x is gone. Okay, these two, we're just going to cross multiply. There is an imaginary 1 here. So you cross multiply, there we go. We square both sides, and we get 2.3 times 10 to the negative 3. So our concentration of hydrogen ions, therefore, from our ice table, we know that x represents concentration of hydrogen ions, is this 2.3 times 10 to the negative 3. Now that we know that value, we can plug that into our pH formula. It's a negative log of the concentration of hydrogen or hydronium. Plug that in right there, and we get a pH value of 2.62. There. So at this point, the first point of your titration, remembering that your titration looks like, titration curve, maybe a straighter line, looks like this, right? Sudden increase, gradual buffering region here, up, more steep, and then plateauing, right? We know that we have solved for this initial point. We know that this pH point, or this point here, measures a pH, and of course this is volume versus pH. We know that in this case it's 2.62. Okay, we have 3 more points. Our next point is after titration is started, but before equivalence. As a reference, let's just say that that's 7. Your equivalence point is going to be up here, so we're going to figure out that pH, and then a few milliliters later, we're going to figure out a pH beyond equivalence. Okay, so that's it for our second video. Our next part is going to start, next video, I should say, is going to begin to solve these 3 other points. Okay, hopefully that helped. Post any questions and stay tuned for the second video.